This is the Chapter 6 pre-class lecture discussing coal. So in the United States, wood was used to be our major source of energy until about the 1960s, when coal became the largest fuel source. 92% of all the coal that's used in the United States today is used for the purpose of generating electricity. Today, Asia Pacific countries are the largest consumers of coal worldwide, followed by North America and Europe. The composition of coal can be approximated by this formula: 135 atoms of carbon, 96 atoms of hydrogen, 9 atoms of oxygen, 1 atom of nitrogen, and 1 atom of sulfur per molecule of coal. And that gives it a molar mass of about 1.908 times 10 to the third grams per mole, meaning that coal is about 85% carbon. That's the mass percent carbon in coal. So if we wanted to calculate the mass of carbon in grams that exists in 1.5 times 10 to the 6 tons of coal, and noting that this quantity of coal might be burned in a typical power plant over the course of 1 year, with these helpful conversion factors, and because you don't see the word metric ton, that means this is a US ton. 1 US ton is equal to 2,000 pounds. 1 pound is equal to 454 grams. So if we burn 1.5 times 10 to the 6 tons of coal, if we multiply the total number of tons of coal by the percentage of coal that's carbon, and of course convert that percent to a decimal, and this number is, to be exact, it's about 85%. It's about 84.96% to be exact. So we convert that percent to a decimal, multiply that by the total number of tons of coal, and that gives us 1.27 times 10 to the 6 tons of carbon. But we need the number of grams of carbon. So we have to convert the tons to grams. One ton is equivalent to 2,000 pounds. 1 pound is equivalent to 454 grams. Your pounds cancel, your tons cancel, and you get 1.16 times 10 to the 12th grams of carbon. In the next part, what mass of carbon dioxide in grams would be formed by the complete combustion of, again, 1.5 million tons of coal, which is 1.5 times 10 to the 6. Well, this is our balance reaction of carbon reacting with oxygen to produce CO2. So if we have 1.16 times 10 to the 12th grams of carbon, we can convert that to moles of carbon by dividing by the atomic mass of carbon. And then we convert moles of carbon to moles of CO2 by using the mole ratio, 1 mole of CO2 per every 1 mole of carbon. And we multiply the moles of carbon by that mole ratio. And then finally convert moles of CO2 to grams of CO2. So 1.16 times 10 to the 12th grams of carbon divided by the atomic mass of carbon, which is 12.01 grams per mole. And then convert the moles of carbon to moles of CO2 by multiplying by this mole ratio. The moles of carbon cancel. And finally, CO2 has a molar mass of about 44 grams per mole. So multiply the moles of CO2 by the molar mass of CO2. The moles of CO2 cancel. So do your math. 1.16 times 10 to the 12th times 1 times 44. Get that product and then divide by 12.01. And that will give you 4.25 times 10 to the 12th grams of CO2. Question 2. Calculate the amount of heat energy in kilojoules released by burning this 1.5 times 10 to the 6 tons of coal. And so the heat Q is going to be equal to the delta H of combustion of coal times the mass of coal. So Q is going to be equal to the delta H of combustion, which is 30 kilojoules per gram, times the mass of coal, which we calculated. I'm sorry, it's not the mass of coal, it's the carbon in the coal that's actually combusting in our combustion reaction. So we need the mass of carbon, not the mass of coal. It's the carbon that's reacting with the oxygen. The mass of carbon, we calculated 1.16 times 10 to the 12th. And so the grams of carbon cancel. So your Q is going to be in kilojoules, and that's going to be 3.48 times 10 to the 13th. That's the number of kilojoules of heat that are released by burning the 1.5 times 10 to the 6 tons of coal. Question 3. Mercury is present in very, very small trace amounts of coal. Mercury can exist in coal at concentration ranges between 50 and 200 parts per billion. So considering our amount of coal burnt in questions 1 and 2, 1.5 times 10 to the 6 tons, calculate the tons of mercury in the coal based on this lower concentration range, 50, and the higher concentration range, 200 parts per billion. So at the lower range of 50 parts per billion, so we're going to take our parts per billion convert to parts per hundred, then convert to a decimal, and then we're going to multiply the decimal by the mass of coal to get the tons. So our conversion factor to convert parts per billion to parts per hundred, 1 times 10 to the second parts per hundred per 1 times 10 to the ninth parts per billion. And then to convert parts per hundred, which is a percent, to a decimal, you just divide by 100. Then you take your decimal and you multiply it by the mass of coal. And that will give you the tons of mercury. So this is our plan for solving this problem. So take the 50 parts per billion, convert the 50 parts per billion to parts per hundred. You get 5 times 10 to the negative 6 parts per hundred. Which is 5 times 10 to the negative 6%. And so we're going to take 5 times 10 to the negative 6%, divide by 100%, and that will give us our decimal. Which is 5 times 10 to the negative 8. And now we take this decimal and multiply it by the mass of coal. And the tons of coal is the same amount in questions 1 and 2, which is 1.5 times 10 to the 6. That gives us 7.5 times 10 to the negative 2 tons of mercury. Then the higher end, the 200 parts per billion, we're going to do the same calculations, except for 50 parts per billion. We've got 200 parts per billion. So now we've got our percent. We're going to take our percent, divide by 100%. We get 2 times 10 to the negative 7. Take that decimal and multiply it by 1.5 times 10 to the 6. And you get that many tons of mercury. So that's your range, 0.075 tons of mercury to 0.30 tons of mercury. That's your range. And that brings us to the end of our Chapter 6 lecture on coal.